Hello everyone, this is Dr.Prashanthi, Assistant Professor, Department of Chemistry from Government Degree College for Women, Karimnagar. Today I am going to discuss about the photochemistry part 3. In the part 1 and part 2, we have seen the introduction and we have seen what are the photochemical reactions, what are the differences between the thermal chemistry and photochemistry, and we have seen the basic laws which govern the photochemical reactions, the two types of laws, Groth-Draper law and Stark-Einstein's law in the first part of photochemistry. And in the second part of photochemistry, we have discussed about the quantum efficiency, that is what is quantum efficiency and what are the types of quantum efficiencies, examples we have seen. And now in this part we will discuss about the photo processes. Let us see what are these. Photo processes. Photo processes are of two types. First one, photophysical processes, and second one, photochemical processes. What are photophysical processes? If the absorbed radiation is not used to cause a chemical change, it is re-emitted light of larger wavelength. The three such photophysical processes which can occur are fluorescence, phosphorescence and chemiluminescence. In the previous parts we have seen that in the primary process only the absorption of radiations takes place and the excitation of the electrons takes place. That is, if an electron or if a substance absorbs radiations of UV light or visible radiations which are considered as photochemical radiations, then the electrons in the substance gets excited to the higher levels. Okay, this process is called as a primary process. Okay, and whether the absorbed radiation or whether after absorbing the radiation, whether the substance undergoes chemical reaction or it may not undergo a chemical reaction. If it undergoes some change or if it undergoes chemical reaction, that is called as photochemical process. If the absorbed radiation do not bring any chemical change in the substance, okay, and if the absorbed light is emitted without undergoing any chemical change, then they are called as photophysical processes. We have three such types of photophysical processes. They are fluorescence, phosphorescence and chemiluminescence. Let us see one by one each. By absorbing radiations, electrons are excited. During the excitations, excited electrons returns to the normal state instantaneously, called as fluorescence, or excited electron returns to the normal state after some time are called as phosphorescence. See, if the absorbed radiation is emitted immediately and if the electron returns to the ground state, then it is called as fluorescence. If the returning of the excited electron to the ground state takes place some time or after some time, it is called as phosphorescence. Let us see what are these in detail. Fluorescence. It is the phenomenon in which a substance absorbs light of shorter wavelengths and emits a part of it instantaneously at different wavelengths without causing any chemical change. It is called as fluorescence, and the substance which exhibits fluorescence is called as fluorescent substance. Suppose for examples we have calcium fluoride, quinine sulfate solution, etc. Or that is a naturally occurring calcium fluoride shows fluorescence. And we have also some more examples that fluorescein, it is a substance which gives yellow green light, and this quinine sulfate solution shows a blue color due to this photo effect. See, what happens here is the absorption of the light energy causes excitation of the electrons that are present in the substance. The excited electrons jump back immediately to the lower level, emitting a part of the absorbed light in the form of radiations of different wavelengths, and these emitted radiations have a greater wavelength than the absorbed light. The energy thus produced in emitting the radiation is smaller, as this process takes place in steps. In some cases, light of shorter wavelength is emitted. In some cases, light of shorter wavelength, that is having higher energy, is emitted because the emitted light contains some energy in addition to the absorbed energy. This is called as induced fluorescence. Suppose if in some cases the wavelength of the emitted radiation is equal to the absorbed radiation, then it is called as resonance fluorescence. Okay, and this effect was first observed by Stokes. Okay, this is first observed by Stokes. Then what are the applications of this fluorescence? Fluorescent tubes, they give bright light. Okay, and this technique is also used in fluorescent microscopes, which are used for testing the condition of the foodstuffs, for detecting of worms, and to study the three-dimensional structures of proteins, etc. These microscopes are used. And next, the radioactive decay is also detected by dissolving the fluorescent substance in the solution or in the solid plastics. And also the aqueous solution of fluorescent gives out intense green color. This is used in detecting the leakage in the water pipelines. In this way, fluorescent substances are used in different methods by this phenomenon of fluorescence. And the next one is phosphorescence. When a substance absorbs radiation of high frequency and emits light even after the incident radiation is cut off, the process is called as phosphorescence. That is, the substance absorbs light and emits it after some time. Even if the radiation is cut off, then also it shows the shows this process that is cut off. The substance shows this phenomenon of phosphorescence. This is called as a slow fluorescence. Examples, we have zinc sulfide, alkaline earth sulfides, etc. And the substance which exhibits phosphorescence is called as phosphorescent substance. This is chiefly caused by ultraviolet and visible light, and this phenomenon is generally shown by the solid substances, and these fluorescent materials are used in luminous clock dials and also in some other objects which are used to glow in dark. Next, photochemical processes. By absorbing radiations, electrons in the substance are excited. We know that by the absorption of radiations, the electrons present in the substance, they are excited. This is the primary process that we know it. During de-excitations, if excited electron returns to normal state after producing some chemical change in the substance, it is called as photochemical processes. That is, we know that the electrons absorb energy. When they absorb energy, they get excited to the higher levels, and there in the higher levels they are unstable, and therefore they again come back to the lower levels by releasing some of the absorbed energy. If the electron returns to the ground state after producing some chemical change in the substance, it is called as photochemical process. And till now we have seen that the electrons are getting excited to the higher levels. Okay, they are de-excited, they are returning to the ground state without any producing chemical change. Then they are called as photophysical processes. And this is photochemical process, that is, they are getting excited, again they are getting de-excited after producing some change in the substance or some chemical change in the substance. This is photochemical process. These processes takes place directly or indirectly under the influence of light radiations. Examples of photochemical processes, we have some examples of photochemical processes here. They are photosensitization, decomposition, double decomposition, isomerization, addition reactions, polymerization reactions, and displacement reactions. Let us see some examples. Dissociation reactions, suppose for example, if hydrogen iodide is there, this in the presence of light, it gets dissociated to hydrogen and iodine molecules. Double decomposition, for example, that is alpha chloroacetic acid on hydrolysis in the presence of light gives rise to alpha hydroxy acid, that is this is OH group is attacking this carbon atom, and this Cl is attacked by the H plus there, so we get HCl. And we have also some rearrangement reactions like malic acid by the absorption of radiations at 2053 angstroms gets converted to fumaric acid, and again the fumaric acid at wavelengths 2830 angstroms, they get again converted to malic acids. These are examples of rearrangement reactions. And next, for addition reactions, carbon monoxide plus Cl2 in the presence of light, they gives rise to COCl2. And for example, polymerization reactions, anthracene, that is C14H10, two molecules of anthracene in the presence of light energy, they gets polymerized to dianthracene. And almost most of the reactions that takes place, we have most of the reactions in which in which the light energy is involved, and they are called as photochemical reactions. And in the part 2 we have seen some examples like photochemical combination of hydrogen and chlorine molecules to give hydrogen chloride, which is of which is having very high quantum yield. And we have also seen example for very low quantum yield, that is photochemical combination of hydrogen and bromine molecules to give rise to hydrogen bromide. All these are the examples of photochemical reactions. Next, let us see what is photosensitization in detail. Photosensitized reactions. The reactions which takes place in presence of sensitizer are called as photosensitized reactions. That is, in some reactions, in some photochemical reactions, the reactant molecules, they do not absorb radiations directly. Instead of those reactant molecules, another substance absorbs radiations and transfers that energy to the reactant molecules, which then undergoes chemical change. Okay. Therefore, they are called as sensitizers. The substance which is used to transfer the absorbed radiation, which absorbs radiation directly and transfers that radiation to the reactant molecules, is called as sensitizer. Sensitizer absorbs the radiations and transfers it to the reacting molecules. For example, dissociation of hydrogen molecule. UV light of wavelength 2537 angstroms does not dissociate hydrogen molecule. So, hydrogen molecule in the presence of light energy or by absorbing radiations, it cannot undergo dissociation, that is dissociation reaction does not occur. But in the presence of mercury vapors, the reaction occurs, that is hydrogen undergoes dissociation to two hydrogen atoms. Here mercury vapor acts as a sensitizer, photosensitizer. So, in this reaction, mercury vapors they first absorb radiations and they get activated. Mercury vapors are first activated by absorbing the radiation, and this mercury vapors then transfers that energy to the hydrogen molecule. Okay, transfers energy to the hydrogen molecule, it gets deactivated, and the energized hydrogen molecule now splits or dissociates into two hydrogen atoms. So, in this way, the dissociation of hydrogen molecule occurs in the presence of a mercury vapor. Next, photosynthesis. So, we have one more example, that is a photosynthesis. Photosynthesis reaction is sensitized by chlorophyll. Here in this photosynthesis reaction, that is we all of us know that photosynthesis is that the plants prepare food by using carbon dioxide and water molecules in the presence of sunlight and chlorophyll. They prepare food, and here the role of the chlorophyll is to act as the sensitizer. The interaction of CO2 and H2O in sunlight to form carbohydrates and oxygen is called as photosynthesis. Both CO2 and H2O do not absorb visible radiation. Actually, CO2, carbon dioxide and water molecules, they do not absorb visible radiations. Instead, chlorophyll absorbs those light radiations, visible radiations, and transfers that energy to this CO2 and H2O molecules, which then undergoes the chemical change and are converted to C6H12O6 carbohydrate, and 6CO2 is released. So, in photosynthesis also, chlorophyll acts as a sensitizer. So, what is sensitizer? A substance which can absorb light and thus which induces a photochemical change without taking part in the reaction. It is called as photosensitizer. It is just acting as a carrier of energy to the reactant molecules. It is photosensitizer, and the reactions which involve these which are induced by photosensitizers are called as photosensitized reactions. Next, chemiluminescence. The phenomenon of emission of visible light in a chemical reaction at ordinary temperature is called as chemiluminescence. That is the reactions, if they emit light at ordinary temperatures, then those that phenomenon is called as chemiluminescence. Suppose for example, light emitted by glowworms. Example is, see, we all of us know that fireflies, that glowworms, they emit light that we can easily see in the dark. This is due to the oxidation of the protein, that is this is due to the oxidation of protein luciferin by the atmospheric oxygen in the presence of enzyme luciferase. So, here in glowworms or fireflies, what is happening there? The protein present in them, that is a luciferin protein which is present in the fireflies, is getting oxidized by the atmospheric oxygen in the presence of the enzyme present in them, that is a luciferase. Okay, due to this they are emitting some radiations which we are calling them as, which we call the process as chemiluminescence. That is, if the radiations are emitted or radiations or visible light are emitted, or if a glow or any light can be seen in a chemical reaction at ordinary temperatures only, is called as chemiluminescence. And suppose for example, next example is greenish glow of phosphorus. Greenish glow of phosphorus, this is due to the oxidation of phosphorus present in the air, in oxygen or air, to form P2O5 at ordinary temperatures. That is when phosphorus is oxidized to phosphorus pentoxide, we can observe some greenish glow or green light is observed. This is nothing but due to chemiluminescence. And sometimes we can also observe that at nights in the oceans we can observe some light or luminescence is observed at nights in oceans. This is due to the decay of some luminous fishes. This is due to the decay of some luminous jellyfish. Okay, because of this also we can observe some glow in the oceans at nights. And over marshy places also we can observe, because of the decay of wood and vegetation, also we can observe chemiluminescence in the marshy places. This is because of the oxidation of this decaying wood, or vegetation which contains some type of bacteria. So in this way, if the visible light, or if the light is emitted in a chemical reaction at ordinary temperatures, that is termed as chemiluminescence. Next, this chemiluminescence can be termed as just a reverse to the photochemical reaction, because in the photochemical reaction the light energy is absorbed and the chemical reaction is happening, and in chemiluminescence the light energy is emitted, or light is emitted in a chemical reaction. Therefore it can also be termed as the reverse of a photochemical reaction. And in chemiluminescence, the excited products emits radiations of appropriate wavelength which lies in the visible region of spectrum. Therefore as it is emitting radiations of wavelength which are in the visible region of spectrum, we are able to see the glow, or we are able to see the phenomenon. Next is a Jablonski diagram. What is Jablonski diagram? Jablonski diagram is a pictorial representation of the energy transitions caused by the absorption of UV radiation by a molecule. See, in all from the starting of the lesson we are talking about the absorption of radiations, excitation of the electrons. Okay, and we know that the electrons, or when a substance absorbs radiations, it gets excited to the higher energy levels, and again it comes back to the lower energy levels. Okay, that is, it is getting de-excitation, So all, and what happens while it is going, or while it is getting excited to the higher levels, and how it is de-exciting to the lower levels, what are the changes that are occurring while it is getting de-excited to the lower levels, all these can be explained by Jablonski by using a diagram known as Jablonski diagram. Okay, therefore it is a pictorial representation of the energy transitions caused by the absorption of a UV radiation by a molecule. When a molecule absorbs UV radiation, it is excited to one of the excited singlet electronic states. Most promotions are from S0 to the S1 state. Okay, for each singlet excited state, there is a corresponding triplet excited state. Okay. Before knowing this, before going into this topic, let us see first what are these singlet electronic states, what is this triplet excited state, let us know. See, most molecules possess even number of electrons in the ground state. Almost all the electrons are paired, that is, even number of electrons means all the electrons are paired. And we know that the spin multiplicity of a state is given by 2s plus 1. 2s plus 1. S means total electronic spin. Suppose if the spins are paired, Okay, if the electron spins are paired, that is if paired, the clockwise orientation of one electron is cancelled by the anti-clockwise orientation of the other electron. Okay, therefore here S is equal to clockwise is cancelled by the anti-clockwise, therefore S is equal to 0. So according to this S 2 into 0 plus 1 is equal to 1. That is, spin multiplicity is equal to 1 means the molecule is in the singlet ground state. The molecule is in singlet ground state. Okay, next, on absorption of a photon, we know that the molecule absorbs one photon of one photon or one quantum of energy and gets excited. So on absorption of one photon of energy, one of the paired electrons, okay, one of the paired electron goes to the higher energy levels. Okay, one of the paired electron, suppose if it is ground state, this is excited state. So one of the paired electron goes to the higher levels, that is gets excited. The spin orientation of the two electrons may be, okay, now the spin orientation may be, that is the electron, it may excites to the, suppose if this electron may excites to the higher levels with the same spin, or it may jump to the higher levels by changing its spin. That is, I will show you. Suppose, okay, suppose if this electron is getting excited to the higher levels by the absorption of radiations, suppose if it excites to the higher energy levels with the same spin, that is in the ground state, whatever the spin it has in the ground state, if it has in the excited state also, then it is termed as a singlet state. Then it is called as singlet state. That is, if the electron is having the same spin both in the excited state and ground state, it is called as singlet state. Okay, and here they don't have the same spin. Okay, here they are having different spins. Suppose if this excited electron, suppose if you take this ground state, excited state, suppose if this electron, by the absorption of some energy, if this electron is getting excited to the higher levels, the spin of this electron is downwards. If it excites to the higher levels by changing its spin, okay, see the difference here, how the spin of the electron of this electron in the ground state and how it is in the excited state. If the electron is having a different spin in the excited state from that of the ground state, it is called as triplet state. It is called as triplet state. Here the two electrons have the same direction of spin. See, the upward direction and upward direction. Okay, so remember, any radiation that is emitting from the singlet state, the radiation that is emitting from the singlet state produces fluorescence, and the radiations that is emitting from the triplet state produces phosphorescence. This is explained by Jablonski in his Jablonski diagram. See here, both these electron in the ground state and electron in the excited state, both are parallel. That is, they are both are in the upward direction only. So in this case, spin multiplicity is, see here, both have the S is equal to half plus half, that is equal to 1. Total spin is 1. So 2 into 1 plus 1 is equal to 3. Here the spin multiplicity of the molecule is 3. That is, the molecule is said to be in the triplet excited state. In the triplet excited state. And if you come to this um, state, here the electrons are oriented anti-parallelly, that is in the ground state it is in the upward direction, and in the excited state it is in the downward direction. Therefore both the spins are cancelled by each other, and total spin is 0, and therefore the spin multiplicity is 2s plus 1 is equal to 0 plus 1 is equal to 1, that is the spin multiplicity is 1, and the molecule is in the singlet excited state, and the molecule is in the singlet excited state. So all these and depending upon this energy of the photon, electron can jump to any higher energy levels. Okay, any higher energy levels, that is from singlet state to, that is from ground state to singlet states and triplet states. Let us see how Jablonski explained all this. So this is the Jablonski diagram. Here the electron that is present in the, see here, the electron that is in the ground state can be excited to any of the singlet states, that is it may be excited to from S0 state to, that is from singlet ground state to S1 excited state, or it may be excited from S0 state to S2 state, or from S0 to S3, or any other higher singlet states takes places. But in most cases the lowest vibrational level of the S1 state is the most important excited singlet state, and this state can undergo various physical and chemical processes. Okay, let us see what are they. The activated molecule returns to ground state by loss of energy through any of the following processes. See, by the absorption of a quantum of radiation, the electron may jump from S0 state to any of the excited singlet states, that is S1 or S2 or S3, any of the states. This step is called as a primary quantum jump. Okay, from S0 to S1 or S2 excited state, S0 ground state to S1 or S2 excited states. And we know that the electron in the excited state returns to the ground state, that is it undergoes de-excitation, and the electron in the ground state can be returned to ground state in different ways. Okay, this process can be shown here. See, the electron, if it is excited to S3 state, it can de-excite, or it jumps from S3 state to S2 state, that is S3 to S2, that is here the loss of radiation, less energy, that means here the energy is lost in the form of heat, that is vibrational transitions takes place from S3 to S2 or S2 to S1. These are termed as internal conversions, that is within the levels only, within the excited singlet states the electron is getting deactivated, that is from S3 to S2, S2 to S1. See, this is called as a non-radiative transition. It involves transition from S2 to S1, S3 to S1, or T2 to T1, or T3 to T1. It does not involve emission of radiation. Therefore, it is called as non-radiative transition. It involves only the emission of heat. So, heat is emitted in this internal conversions only. Next, the energy of activated process may be lost through either of the following process. See, the electron from the excited singlet states is getting de-excitation to the ground state. Okay, and we are calling it as a not to the ground state, from excited S3 state to excited S1, or excited S2 state to excited S1 state. Okay, this involves only the emission of heat. Okay, no light radiations are emitted in this process. Okay, how the heat is means how the energy of the activated molecule is lost in this process. It is by two methods. Internal conversion, that is in this process energy is lost in the form of heat. We have seen already, that is it involves transition from S3 to S2 or S2 to S1 or T3 to T2, T2 to T1. This occurs in less than 10 power minus 11 seconds. And the next method is inter-system crossing. Another method is inter-system crossing, that is in this process energy is lost through the transition between states of different spins. See here in the internal conversion means from S3 to S1 or S2 to S1 is taking place, that is de-excitation is taking place. But inter-system crossing means the singlet excited state singlet excited state is converted to triplet state. These are spin forbidden transitions, that is excited singlet state is converting to excited triplet state. Okay, this process is called as inter-system crossing, that is conversion of excited singlet state to excited triplet state is called as inter-system crossing. Okay, S3 to T3 or S2 to T2 or S1 to T1. These transitions are forbidden. The transitions between singlet states to singlet or triplet to triplet state only are allowed transitions. These are forbidden transitions. Next, radiative transition. Radiative transition means the name itself indicates that they emit radiations. Here the radiations are evolved. This involves transition from S1 to S0 or T1 to S0. Let us see the diagram once again. See, we have seen that the electron is getting excited to from S0 to S1, S2, S3. Okay, again it is de-excited from S3 state to S2 or S2 to S1 state. We are calling them as internal conversions. Suppose if the singlet state is getting converted to the triplet state, we are calling it as inter-system crossing. Okay, it is called as inter-system crossing. And these systems evolve heat only, they are not evolving radiations. Therefore, they are non-radiative transitions. And the de-excitation from S1 state to S0 state, S1 state to S0 state, or see here T1 state to S0 state, T1 to S0 state, they involve the emission of radiations, that is from S1 to S0, T1 to S0. Here the radiations are emitted in these transitions. Therefore, they are called as radiative transitions. Okay, and the radiations that are emitted when the electron gets deactivated from S1 to S0 is called as a fluorescence. Okay, and the radiations that are emitted when the electrons are getting deactivated from excited triplet state to the ground state, then the radiations emitted or the process is called as phosphorescence. Okay, and if you remember, we also call phosphorescence as slow fluorescence, because here the radiation or here the electron is directly getting deactivated from S1 to S0, okay, in the fluorescence. But in phosphorescence, what actually happening is the electron from S1 is getting converted to is changing its state, that is a singlet excited state is converted to triplet state, triplet excited state, and from triplet excited state the electron is getting deactivated to S0 state, that is ground state. Therefore, phosphorescence process takes place for a long time even after the radiation is also cut off. therefore it is also called as slow fluorescence. Next, see, fluorescence. Radiative transition can be of two types, that is the emission of radiations from S1 to S0 is called as fluorescence. This occurs in 10 power minus 8 seconds, and phosphorescence is the emission of radiation from T1 to S0 state. It is called as phosphorescence. It is a forbidden transition that we have seen now, that the transitions from triplet state to the singlet state are forbidden transitions. Only the transitions between two singlet states or two triplet states are only allowed transitions. In this way, Jablonski explained the de-excitation of electrons in a photochemical reactions, how they are getting de-excited and what is happening during the process, which involves two types of transitions, that is non-radiative transitions, in which the radiations are not liberated, or they are not released in the process. Heat is liberated in this process, and again it is of two types, that is internal conversion and intersystem crossing. And also we have second type, radiative transitions, which involves the emission of radiations, and this is also of two types, that one is fluorescence and the other one is phosphorescence. And with this I conclude the topic of photochemistry part 3, and in this lecture we have discussed about the photo processes, that is photophysical processes, photochemical processes. Under photophysical processes we have discussed about fluorescence, phosphorescence and the chemiluminescence, and we have seen some examples of photochemical reactions. And next we have seen Jablonski diagram, which explains the excitation of electrons and de-excitation of electrons in a substance. What are the ways we have seen in this Jablonski diagram. And in the overall topic, this is a very important lesson for final year chemistry students in the 5th paper of final year. The laws of photochemistry are very, very important for the final examination point, and quantum efficiency is important, and the abnormal quantum efficiencies, that is the reactions having high quantum yields, the reactions having very low quantum yields, these are also very important. And next for short answer questions, the phenomenon of fluorescence with examples, phosphorescence with examples, and chemiluminescence with examples is important. And the last Jablonski diagram is also very important for the final examination point. With this I concluded today's session. Thank you.